everyone. Welcome to online lecture series of electronic devices. I am Dr. Sapna Katiyar, Professor in Electronics and Communication Engineering Department at ABES Institute of Technology, Ghaziabad. This is lecture number 16 and today's topic is optical absorption and luminescence. So, in today's lecture you are going to study about two topics. First is optical absorption, then we are going to discuss about the luminescence. Let us begin with the optical absorption. What is this optical absorption and how to define it? See, before starting this, you must understand what is the term excess of carriers. You used to study this particular term at number of times when you are studying the devices. What do you mean by this? Excess of carriers, this term is used for the electrons and holes. See, in the case of the semiconductors, what are the carriers? The charge carriers are electrons and holes. Depending upon the type of semiconductor, whether it is a N-type semiconductor or a P-type semiconductor, the charge carriers, the name vary. Means in case of N-type semiconductor, the majority charge carriers are electron. In case of N-type, P-type, the majority charge carriers are holes, while minority charge carriers are holes in case of N-type semiconductor and it is electrons in the case of P-type. So, this term is commonly used where with reference to the electrons and holes which are excess of their thermal equilibrium values. You must remember for the thermal equilibrium values we used to represent N naught and P naught. And excess carriers can be created by various mechanisms. One is the optical excitation, second is the optical bombardment, and there are various other mechanisms also. So, excess carriers are created actually by a certain mechanism. Now, optical absorption means what? Optical absorption means absorption of electromagnetic radiation of light by semiconductor material. When light is going to impart on a semiconductor material, then this optical absorption process follows. And optical absorption, it depends on the property of the material. How much absorption will take place? It entirely depends upon the property of that particular semiconductor material. You can see over here in this particular diagram, valence band and conduction bands have been shown. Valence band, in the case of the valence band, many electrons you can see over here, these solid dots. And in case of conduction band, many empty states are available. What will happen when a photon will excite, hit to this particular semiconductor if this is having an energy h nu which is greater than Eg. Eg is the band gap between the valence band and the conduction band. See, this particular thing we can observe in two cases. Let me write case 1, when h nu, this is greater than Eg. This particular case you can observe over here. Now, what will happen here? The electrons which are available in the valence band, these electrons will excite, they will move from the valence band to the conduction band. As you can see over here, they will move from point number 1 to 2 because of getting this much of the energy. Now, because of the scattering mechanism which occurs in the crystal itself, they will lose certain amount of energy and will come to this particular point, let us say point number 3. And after a certain time, this electron falls from conduction band to the valence band, means from 3 to 4. So, this process where this electron moves from point number 1 to 2, this is known as the creation of electron hole pair. As electron moves from the valence band to the conduction band, it creates a vacancy. You can see this one, and this vacancy is known as a hole. So, because of this optical absorption, electron hole pair is created, and when electron moves from conduction band to the valence band, you can see electron jumps from here and it occupies a state which is available. The vacancy which is available, that is known as a hole, means this is the process of the recombination. So, this one is the generation and this is recombination, and both the processes occur simultaneously. Second case, you can observe the case 2, when this energy h nu, this is less than Eg. Now, this particular energy is not sufficient so that the electron can move from the valence band to the conduction band. That is why some of the material looks like transparent. How to calculate the absorption coefficient alpha? You know the optical absorption, but if you have to calculate the optical absorption coefficient, mathematically how to write it down? See, if a beam of photons with energy h nu greater than Eg, it falls on a semiconductor as I have shown you in the case, then some of the predictable amount of energy is absorbed while rest of the energy is transmitted. So, absorption of energy depends upon the nature of the material only, how much energy is being, means if the transmitted energy, incident energy is I naught, out of that IT is the transmitted, some of the energy may be lost. So, absorption totally depends upon the nature of the material. Ratio of the transmitted light to the incident light, IT is the transmitted light, I naught is the incident light. This ratio depends upon the two factors, one is the photon wavelength, other is the material thickness, how much thickness for that particular semiconductor is. Here you can see, here a monochromator is being shown. With the help of this monochromator, incident light I naught is being imparted on the semiconductor sample. The thickness of the semiconductor is T, and then it is going to be like observed by a photodetector. Photodetector is used to identify what is the intensity of the transmitted light. IT is the intensity of the transmitted wave over here, and for calculation a small thickness dx is being taken at a distance x. If you are moving along a distance x, a small portion is being taken over here. So, monochromatic beam of light is allowed to fall on this particular semiconductor, and the photodetector measure the intensity of this particular transmitted light, how much intensity, and you must remember that the value of IT will be less than I naught, as well as this particular incident beam is crossing through a semiconductor, its intensity will decrease certainly. Now, as I have told you, when beam passes through the semiconductor, the intensity decreases. Let us consider a small distance dx at a distance x from the surface of the sample, because you need to derive a mathematical equation. If Ix is the intensity of the beam at a distance x, then degradation of intensity. See, if I naught is the intensity which is falling on a semiconductor and it is passing through a semiconductor bar, and after that particular end, if you are going to calculate the intensity, definitely it is going to decrease. Now, what is that particular decrease in the intensity? See, minus sign is being like taken over here because degradation is there, decrease in the intensity, d upon dx of Ix. Ix is the intensity which you are calculating observing along the x-axis, and minus is the term which denotes the degradation. This is proportional to the Ix intensity. At the same time, you have to introduce a proportionality constant. Now, alpha is a proportionality constant which is being introduced over here, and this alpha is known as a optical absorption coefficient. So, what is this particular term? Minus d of dx upon Ix. It is like alpha into Ix. Now, you have to simplify this particular equation. You have to find out the solution of equation number 1. So, solution of equation number 1 can be given as what? Ix is I naught e raised to the power minus alpha x. This will gives you a exponential solution. I naught is the incident light intensity. If IT is the intensity of transmitted beam, then we can write down IT is the intensity of the transmitted beam, then Ix can be written as what? IT. I naught is the incident transmit beam intensity, I naught e raised to the power minus alpha t. So, from here you can calculate this ratio IT upon I naught as I have discussed, and this ratio is what? E raised to the power minus alpha t. So, this is how you can calculate, you can identify, you can measure the absorption coefficient, and this absorption coefficient is denoted by alpha. I hope this particular point is also clear to you. Now, let us discuss the variation of optical absorption coefficient alpha as a function of photon energy. Optical absorption alpha varies with respect to the photon energy. Two cases I have shown you. If the photon energy is higher than the band gap, what will happen? If the photon energy is less than the band gap energy, what will happen? How to plot this particular variation? So, this particular variation can be plotted as, you can see on the x axis this photon energy is being taken, while on the y axis the absorption coefficient is being taken, and here the behavior have been plotted over here. So, this is actually the dependence of absorption coefficient alpha for a semiconductor on the wavelength. You can observe, you can understand the overall behavior in three different cases. Case 1, you can see this particular portion, initial portion. Here you can see this particular value of alpha, this is very small. So, when h nu, this is less than this band gap, this Eg is the band gap. So, when this particular value is less than the band gap, you can see the value of alpha is very small. It means most of the light is transmitted through the sample, and sample looks like transparent over here. So, and you can see absorption is very less, absorption coefficient value, this is very less. Second case, you can observe when it approaches to Eg, this photon energy h nu, it approaches to band gap energy. What will happen in that particular case? Now, photon energy increases and the value of alpha is also increases. You can see this particular curve over here. So, when photon energy increases, it approaches to the Eg, band gap energy, it means value of alpha is also increases. Now, the third portion, when the photon energy is greater than this band gap energy, in this particular case you can see the value of alpha increases sharply. So, here value of alpha increases sharply, then it breaks the covalent bonds and create electron hole pair. It means semiconductor becomes opaque at this particular frequency. So, this is how you can relate the photon energy with the absorption coefficient, how it varies, and you can plot its behavior. So, I hope now this particular plot is also clear to you. Now, let us come to the another topic, which is the luminescence. What is luminescence? Luminescence, you must have heard, you have studied the CRT in your school, you used to observe the behavior of LED, how it works. So, the very fundamental factor is the luminescence. See, many semiconductors absorb energy in some form or in other form. So, what happens when they absorb energy? Some of the amount of energy is being absorbed and the remaining may be reflected back. So, the general property of light emission is known as the luminescence. You can define it. What is luminescence? Luminescence is the general property of the light emission. And luminescence, it is a two-step process. If you observe the overall working, the behavior, it is a two-step process. The step 1 is the excitation of the system. Step 2 is the subsequent emission of the photon. So, these two steps parallelly, subsequently occur in the case of the luminescence. So, this is how you can explain its working. Depending upon the excitation mechanism, luminescence is of three types. See, in the case of the excitation of the system, depending upon the material, there are various types of, you can define, there are various categories of luminescence. The three major categories are photoluminescence, cathodoluminescence and electroluminescence. I hope you are very much clear with all these three terms, but let us revise if you are not aware with. What is photoluminescence? Photoluminescence is if the carriers are excited by photon absorption. If photon energy is being imparted to a semiconductor, that energy is being absorbed and the carriers are excited. As I have discussed one case where the carriers are excited and they are moving from the valence band to the conduction band. So, in that particular case, when the carriers are excited by the photon absorption, then the type of luminescence is known as a photoluminescence. Second is the cathodoluminescence. If the excited carriers are created by high energy electron bombardment of the material. You must note down this particular statement. If the excited carriers are created by the bombardment of the material, as you have studied the CRT, that particular case. So, that is the case of the cathodoluminescence. The third is the electroluminescence. If the excitation occurs by the introduction of the current into the sample, then the type of luminescence is electroluminescence. I hope now you will be able to differentiate among all these three. What is photoluminescence, what is cathodoluminescence, and what is electroluminescence. So, depending upon the excitation mechanism, in all these three cases the excitation mechanism are different. So, this is how you can remember it. Several semiconductors shows the properties of luminescence, especially direct band gap compound semiconductors, and some of the examples of direct band gap semiconductors have been listed over here. You are aware with the direct band gap semiconductors. Direct band gap semiconductors are those semiconductors where electrons which are available in the conduction band is directly fall into the valence band, means the conduction band minima and valence band maxima align with each other. The value of k, the vector, the value of k is same. That is the direct band gap. So, many semiconductor materials are there which shows the properties of the luminescence. Now, let us discuss each and every type of luminescence, which is the photoluminescence, cathodoluminescence and electroluminescence in detail. First is the photoluminescence. What is this? When light falls on a semiconductor material, the charge carriers electron hole pairs are generated. We have discussed already, means when light falls on a semiconductor material, then there will be a movement of the charge carriers, there will be a charge carriers excitement, and some electrons will move from the valence band to the conduction band. It means they are creating a vacancy in the valence band, and this particular process is known as a generation, and this is nothing but the electron hole pair generation. And these charge carriers are produced by two ways: band to band transition, which is known as the intrinsic, or transmission involving forbidden energy levels, which is the extrinsic. You can understand with the help of this particular diagram. See, here this light is being like imparted, falls on a semiconductor. If electron moves from this point A to the point B, there is a direct transition band to band. So, this is known as a intrinsic. In the second case, you can see the transition is from this point A to B via this intermediate level C. First it is falling from A to C, then from C to B, and C is the forbidden energy level. This may be a trap. So, accordingly this type means this is the case of the extrinsic. This is the case of the extrinsic semiconductors, right? Emission is of two types: direct or fast process, which is the fluorescence; slow process, which is the phosphorescence. So, there are two ways of the emission: direct or fast process or slow process. In fast process, emission of photons stops within approximately 10 raised to the power minus 8 seconds after the excitation is turned off. So, this is the case of fast process. Why this particular time interval 10 raised to the power minus 8 is taken? 10 raised to the power minus 8 is taken because this is the lifetime of an atom. Atom remains in the excited state for this particular duration for 10 raised to the power minus 8 seconds, and after that it returns to its original state. So, in fast process it remains, while in the case of slow process emission occurs even after the excitation has ceased. even if the excitation has ceased, this particular process is stopped, even then the emission is occurring. That is the slow process. So, I hope now these two types of emission, this is also clear to you. Let us discuss in detail the excitation and recombination mechanism. See, excitation, there is a gap, there is a time in between the excitation and recombination. It does not occur at the same instant of time. You can understand with the help of this particular diagram. You can see this is the valence band, this is the conduction band. In the case of the valence band, you can see it is filled with the electrons. The conduction band has many empty states. So, in this particular process, the first step is an incoming photon with energy h nu 1, which is greater than Eg. This is absorbed. Now, what will happen? You can see now electron will move from this valence band. From this point, it will reach to the conduction band at point number 2. It means now when electron moves from here to the conduction band, a vacancy is being created. This vacancy is known as a hole. So, this is the generation of electron hole pair. Now, what will happen? This excited electron gives a certain energy to the lattice, and then it reaches to this particular point, point number 3. After that, what will happen? The electron, you can see there is a level ET, trapped level. Then this electron can be trapped by a impurity level, which is ET, means it reaches to point number 3 to point number 4. Now, electron remains trapped until and unless it is not thermally re-excited to the conduction band, means from point number 4 to 5. When it is thermally re-excited from trap level to the conduction band, this particular process is being shown. And finally, what will happen? There will be a direct recombination from this point number 6 to 7. Means electron will directly fall from the conduction band to the valence band and recombination will take place. And in this particular recombination, it is giving off an energy which is h nu 2. So, here you must remember that the value of energy h nu 1, this will be greater than the energy which is releasing it off, h nu 2. This is how generation and recombination takes place, and there is a time gap between these two events. Second is the cathodoluminescence. What is cathodoluminescence? The excitation of luminescent material by electron bombardment is known as cathodoluminescence. See, recall the things you have studied in the case of the CRT. The major principle of CRT is the selective excitation of a phosphorescent screen by a beam of energetic electrons within a vacuum tube. Just let us recall the CRT. Here you can see a structure of the CRT cathode ray tube. You can see there is an electron gun and it consists of a like cathode, anode, heater. There is a set of accelerating plates, there is a set of deflection system, and there is a like screen, and on the back side of the screen a phosphorescent material is being like applied over here. What will happen? When a beam of electron, as you can see over here, when a beam of electron is being generated by the electron gun with the help of the accelerating anodes, they are getting the potential acceleration increased, and the function of this deflecting system is it deflects the electron beam horizontally and vertically. There is a set of horizontal deflection plate that deflect the electron beam horizontally. There is a set of vertical deflection plate which deflect the electron beam vertically. Accordingly, that particular electron beam is going to strike the screen. If electron beam strike at this particular point, now what will happen? A bright point, a bright spot will appear. This is because of this phosphorescent screen. Because the electron beam, which is consisting of electron, very high energy of the electrons, they are striking with the wall, striking with the screen, and they are releasing of certain amount of energy in the form of the light. That is why this bright spot is being appeared. Light is giving off over here. This is how you can explain its function. Like you can clear, as you can see in the case of the TV screen also, how a complete scene is being formed. There is a scanning of complete frame. like this particular electron beam is arriving, and that particular electron beam scans the whole frame from left to right, then from top to bottom, as if you are writing in your notebook. You used to write from starting from left, goes to the right, then second line, then third line. When one complete page is scanned, it means that is the completion of one frame. This is how this scanning process takes place. The similar principle, this electron beam strike, it will hit the screen on a certain point, giving off certain energy. It means what happens over here? Here the excitation is because of the electron bombardment. So this type of luminescence is known as a cathodoluminescence. You must note down all of these points as well. So I hope now photoluminescence is clear, cathodoluminescence is also clear. Principle you must remember, this is the selective excitation. Now let us discuss the third type of luminescence, which is electroluminescence. Recall what I have told you, the case of the electroluminescence, how it is being categorized. When the luminescence occurs due to the introduction of the electric field or current, it is known as a electroluminescence. See, depending upon the nature of the excitation, the luminescence is being categorized into three categories. Electroluminescence is when this particular luminescence occurs because of the introduction of electric field or current, right? So this is the electroluminescence. The first electroluminescence effect was observed when a phosphorus powder like zinc sulphide, it is placed in a plastic or gas capsule and it was subjected to an electric field, because here the behavior because of the electric field and current is going to be observed in this particular case, in the case of electroluminescence. Light was given by phosphorus and the efficiency was very low. Here in the case of this electroluminescence, it was observed that the efficiency of this particular system, efficiency in this particular case was very, very low. So there was a challenge to increase the efficiency to make the system good. So electroluminescence can also result from tunneling into forward biased or reverse biased junction as well as avalanche excitation. So there is one more way, because in that particular, in the previous case, the efficiency was very, very low. That is why the another mechanism can be observed, and this explains how the electroluminescence from tunneling into forward biased, into reverse bias junction, and in the case of the avalanche excitation. You will be studying the forward biased behavior of the PN junction, reverse biased behavior, what is avalanche, what is Zener. So in that particular case, but you must remember here the excitation mechanism is because of the introduction of the current and electric field. So this is how you can explain the electroluminescence. In the case of the laser injection in luminescence, it can be observed in the case of the light emitting diode. So I hope now you can explain all the three types of luminescence and how they are going to be categorized. Some of the important points which you must remember and we have discussed in today's class. Optical absorption means absorption of electromagnetic radiation of light by semiconductor material. Optical absorption depends upon the property of the material. Excess carriers can be created by various mechanisms. Some of the mechanisms are like optical absorption, bombardment, electron. Depending upon the excitation mechanism, there are three types of luminescence which is known as photoluminescence, cathodoluminescence and electroluminescence. In photoluminescence, carriers are excited by photon absorption. In case of cathodoluminescence, the excitation is because of the electron bombardment, and when the luminescence occurs because of the introduction of electric field or current, it is known as the electroluminescence. I hope all these points are now very much clear to you. Thank you so much for watching this video.